NASA may have just found the strongest evidence yet that life once existed on Mars, and it is hiding in a rock covered with tiny dark spots that look a lot like fossilized microbial waste. Those specks are only a couple of millimeters across, but if the current interpretation holds up, they could rewrite how we think about life in the universe. Not with drama and neon headlines, but with patient, testable chemistry. The story starts in Jezero Crater, an ancient impact basin on Mars that used to hold a lake billions of years ago. From orbit, you can see the ghost of a river system frozen in stone, a carved channel leading into the crater, and a fan-shaped delta where the water once slowed down, dropped its load of sediment, and quietly built a layered archive of the past. When NASA chose a landing site for the Perseverance rover, they aimed straight for the mouth of that river, because wherever water slows and sediments pile up, remnants of anything that lived there are most likely to be trapped and preserved. Perseverance is essentially a mobile geology lab on 6 wheels. It drills cores, zaps rocks with lasers, and carries instruments that can sniff out elements, minerals, and organic molecules. For 3 years, it has been crawling across the old lakebed, reading the landscape like a slow, patient reader working through a thick textbook. Then, one particular rock showed up in the cameras looking just strange enough to pull everything into focus. Across its pale, fine-grained surface ran a pattern of dark specks and blotches, tiny poppy seeds and leopard spots scattered in repeating lines. Zoom in, and those shapes are still small, barely the width of a grain of rice, but they are organized in a way that does not look random or like ordinary stains. They track along bedding planes, cluster where the sediment once changed, and seem to respect the structure of the rock rather than ignoring it like splashes. Slow down. Perseverance extended its robotic arm, pointed its instruments, and started taking the rock apart with light and math. The sensors showed that this is sedimentary rock, built from mud and silt that settled slowly in water, then compressed and cemented over millions of years. That already matters because sedimentary rock can act like a natural filing system for fossils. It keeps delicate structures intact where volcanic rocks would simply melt and homogenize everything. The dark spots themselves turned out to be rich in 2 iron-based minerals, vivianite and greigite, and the same rock holds an unusual concentration of organic compounds. On Earth, that combination almost always points to biology. When microbes feed on decaying organic matter in cold, low-oxygen environments, they tend to leave behind exactly this kind of iron-rich residue. Layer soft, wet sediment on the bottom of a lake, seed it with organics, let microbes run their quiet economy, and after enough time you can end up with patterns very much like these. Those organics are not exotic chemicals unique to Mars. They are built from the same core ingredients that make up the bulk of a human body: carbon, hydrogen, oxygen, and nitrogen, plus a supporting cast of sulfur and phosphorus. Others can form in place when simple molecules are given energy and time. What matters is not that Mars had complex chemistry, which we already expected, but that in this specific rock, the building blocks of life and the suspected waste products of life sit in the same tiny neighborhoods. At this point, it becomes tempting to declare that we have found proof of life, and that is exactly the temptation NASA refuses to indulge. For most viewers, the important part is not the jargon, but the simple question: could something real have lived there once? Their language is careful on purpose, shaped by earlier moments when excitement ran ahead of the evidence. In 1976, the Viking landers carried an experiment that was supposed to be simple and decisive. Scoop up Martian soil, add nutrient-rich water labeled with a tracer, and watch for gas given off as microbes metabolize the food. The instruments detected a release of carbon dioxide right on cue, which looked exactly like the signal you would expect from microbial activity. Context mattered. Then other instruments reported no trace of organic molecules at all in the same soil, which is very hard to reconcile with a thriving microbial community. Over the following years, chemists and geologists showed how Martian soil chemistry alone could plausibly generate the CO2 signal without any biology involved. The Vikings had revealed something interesting about the planet, but they had not proven that anything was alive. A couple of decades later, a meteorite from Mars found in Antarctica seemed to contain tiny worm-like shapes inside minerals. A president stood at a podium and spoke to the world about possible Martian life. As more data came in, those shapes turned out to be explainable by non-biological processes, the result of water and rock interacting under certain conditions with no living cells required. In conference rooms and review panels, younger scientists feel the weight of that history. One early career researcher scrolling through the new Perseverance data could see the pattern forming in her mind, could feel the thrill of this might really be it, and still chose her words carefully when she spoke up. Rather than announcing a conclusion, she pointed to the alternative explanations that would have to be killed off first before anyone should use the word proof. That is why the current Leopard-Spot rock is being treated as a case for the prosecution instead of a foregone verdict. The team started by asking what else, besides microbes, could paint this pattern of dark, iron-rich spots through a sedimentary rock. One option is a high-temperature process. Very hot water, somewhere between scalding and near boiling, moving through the rock and rearranging minerals as it goes. But the minerals in question, like vivianite, simply do not survive prolonged exposure to that kind of heat. Cook them, and they break down. The pattern in Jezero looks more like something that formed in cold, quiet conditions. Another possibility is extremely acidic water slowly soaking through the rock over long periods. Acid can carve dramatic pathways and concentrate minerals where you least expect them. Yet the same sample contains olivine, a mineral that does not tolerate strong acid very well. If corrosive fluids had dominated the history of this rock, the olivine should have been destroyed or altered beyond recognition. And it is still there, stubborn and intact. Bit by bit, the simple chemical explanations lose their footing. Meanwhile, lab experiments on Earth give the biological interpretation more muscle. When scientists replicate calm, low-temperature, low-oxygen environments, rich in organics, and seed them with microbes, they often see iron minerals and organic residues gather into similar tiny spots and streaks. Change the temperature, ramp up the acidity, or strip away the organics, and the pattern collapses. Keep the conditions within the narrow band that microbes like, and the spots return, as if the system is telling you what it prefers. One student, overwhelmed by a flood of online thumbnails screaming about alien proof and secret fossils, finally closed the recommendation feed and opened the actual research paper instead. The tone inside was almost shockingly calm compared to the headlines outside. Step by step, the authors walked through their measurements, their assumptions, the tests they had run against non-biological explanations, and the places where uncertainty still sat. Reading that, the student realized how different real discovery feels from the noise that claims to report it. The quiet conclusion is this: the simplest remaining explanation that fits all of the current data is that microbes once lived in that Martian lake, fed on organics, and left behind mineral scars we can still see today. It is not the only possible explanation in the universe, but it is the one that now seems hardest to dislodge without inventing more and more complicated chemical gymnastics to replace a straightforward biological story. That is why many scientists now say there probably was life on Mars, not as a slogan, but as a careful summary of where the evidence currently points. Zooming out, that single rock has consequences far beyond one crater. If both Earth and Mars developed life around the same broad window of time, then life may not be a rare cosmic accident. It might be what naturally happens when you mix water, organics, and time under the right range of temperatures and pressures. Instead of asking, how did this miracle happen once? The better question becomes, how often does this process start wherever conditions allow? Astronomers have already cataloged thousands of planets around other stars, many of them sitting in their system's temperate zones where liquid water could exist on the surface. Combine that census with a strong hint of ancient Martian microbes, and the idea that Earth is uniquely alive starts to look less like a sober assessment and more like a kind of quiet arrogance. It becomes more reasonable to assume that microbial life is common, that planets and moons throughout the galaxy have hosted their own bacterial ages, and that some of them may have gone much further. All of this makes the next steps around that Leopard-Spot rock feel even heavier. Perseverance can only go so far. To truly test the biological hypothesis, Scientists want to bring samples of that rock back to Earth, into labs where they can push the material through an arsenal of microscopes, spectrometers, and other tools no robot could reasonably haul to Mars. Sample return is expensive, technically brutal, and politically fragile. The plans sketched out over the past few years involved a second lander, a small rocket to launch the sealed tubes into Martian orbit, and an orbiter to catch them and carry them home. Costs climbed, timelines stretched, and the project ran into the hard wall of finite budgets and shifting priorities. At the same time, China has been developing its own Mars sample return mission, with ambitions to land, collect rock, and deliver it back to Earth on a similar schedule. Some people worry about who gets to be first, who announces the final verdict on Martian life, whose flags and logos appear in the history books. From the perspective of the microbes that may have once lived in Jezero, none of that matters. From the perspective of science, what matters is that the samples make it back intact, uncontaminated, and available to be examined and re-examined by teams all over the world, not hoarded as trophies. The universe does not care which agency's acronym appears on the press release. A senior engineer who had spent years in an online community where every discussion about Mars turned into a fight over rockets and national pride eventually noticed that he never logged off those threads feeling smarter. The debates did not sharpen ideas, they dulled them, burying good questions under loyalty tests. In the end, the rock with the leopard spots represents two related truths. First, the physical one, that Mars was once wetter, more chemically rich, and more biologically promising than we gave it credit for, and that it may have hosted its own era of microbial life. Second, the human one, that our understanding of the universe advances not because we shout the loudest about miracles, but because we are stubborn enough to test every beautiful idea against reality, even when it risks shrinking the story we want it to tell. Somewhere in Jezero Crater, a cigar-sized core of that rock now sits in a metal tube on the surface, waiting for a ride. It is just one sample among many, but inside it may be the clearest record we have ever held of life that did not start on Earth. Whether it is a true fossil or a remarkably persuasive chemical impersonator, bringing it home and opening it up with all the care we can muster will do what honest data always does: sharpen our questions and force us to grow up just a little more in how we see our place in the universe.